As Robert already introduced, I will tell you something about laser ultrasound and its potential to contribute to the sustainability in metal production and processing. The talk will be roughly split in those parts. So at the beginning, I will show you some rough numbers about the Green Deal and the arising needs for the steel production. Then I will introduce laser ultrasound to you as a supportive method for these related processes. And I will also show you examples of the contributions of laser ultrasound to the current challenges in the production and processing of, in particular, steel and also aluminum. Okay, so the Green Deal and some numbers. As you probably know, so the greenhouse gas emissions are increasing, and these are numbers reaching to 2019, but I think it's still on the same way, unfortunately. So we have 64% of carbon dioxide equivalents arising from fossil fuel and in industry. There are also other contributors, but as you see, the main part comes from fossil fuel and industry. And the Paris Agreement from 2015, which is still valid, suggests or requires or requests the reduction of the emissions by 55% by 2030, and so compared to the levels from 1990. And by 2050, we should be climate neutral. So there is quite a challenge that we all know about. And if we have a closer look at the greenhouse gas emissions on those sectors here, you see the main cause is still the power production, transport, and also the industry. But the blue part that you see on the bottom here is only the steel production. And these are 8% of the global greenhouse gas emissions. So the steel production has a great challenge. It needs to be switched to H2-based production, as you see here. And it also includes the increased use of scrap. And this is one of the points where laser ultrasound could be a supportive or will be a supportive method and can be, is applicable there. And also steel processing would contribute to the greenhouse gas emissions if there is an early quality assurance in early process steps. So the characterization of the microstructure, for example, elastic properties, and the detection of defects and materials, defects in materials and joints. This is also an area where laser ultrasound is applicable and can contribute. I'll show you the example of Austria in particular. We have here 15% of all CO2 emissions are caused by a single steel producer, the voestalpine in Austria. And so the goals, as I told you, are reduction to 2030 and also, and finally, climate neutrality until 2050. So the major needs are the transformation to hydrogen and also more scrap. So the challenge by using more scrap is that you have a lot of undesired accompanying elements in there which change the properties of your steel. So this is where laser ultrasound can contribute, because it's a high throughput method and it can establish correlations between the laser ultrasonic measurement results, the data, and the phase transformation, for example, and the phase fractions. Also the grain size distribution and grain growth, and texture and recrystallization kinetics. So in this area, laser ultrasound can contribute because it's a non-contact method, and we can do in situ analysis there to support the steel industry to get greener and to have to fulfill actually the climate goals that we have set. As many of you are new to laser ultrasound, I would like to introduce the basics of it. So the principle is that there is an excitation laser which shoots a short pulse on the surface of the sample, and there is a thermal expansion and ablation which generates ultrasound at this point, which travels then in various directions. So through the whole sample, and a part of it comes back either from defects or also from the microstructure itself. And the echoes are then detected by a laser vibrometer. So these are special vibrometers which are very sensitive to vibrations also on rough surfaces. What you see here is the case where the excitation laser heats up the surface shortly. In the top green area, you see the pressure wave, so and the shear waves going back, starting to propagate from this excitation point here. And in the lower half, you see the thermal diffusion process, which is very local and which is transient and so there is no big temperature impact on the sample. The advantages of laser ultrasound are obvious partly. So it's fully contactless, it allows remote operation, it has a minimal influence on the excited waves, it can be operated in harsh environment, also in the steel production, for example. Automation is possible, and there is a good accessibility by the laser beams. And we have a wide bandwidth of the signals that we can then evaluate from around below 1 megahertz up to 50 megahertz in usual industrial applications. So those excitation lasers, here are some examples of possible excitation lasers so that you get an imagination or some impression of the equipment which is used. Either lasers which have a very high repetition rate from one shot to the other, but a lower power per pulse. And for a special application, we also need high power lasers, which have then a bit lower repetition rate. On the detector side, the laser vibrometers, the range goes from, well, industrial vibrometers, which are robust and can be adapted for special applications. But if we have very specific requests, we also build these systems on our own. And from this set of hardware, we develop methods and systems fulfilling the needs and our partners' requests. So where are now the specific contributions where this laser ultrasound method can contribute to the steel production? What you see here is our thermal simulator. It is actually a dilatometer, which has a vacuum chamber up here. And also a linear stage if we want to simulate rolling processes, for example. And here the laser ultrasonic system is applied. You see here the measurement head and the excitation laser here on the back. So we can do lab scale measurements here with a very compact dilatometer system. What we do in detail with this is the following. The vacuum chamber, where you see here the coil, where we can place a sheet metal on it, and we heat it through some defined temperature curve, and we can look with laser ultrasound in situ on this sample. So we can observe the changes of the ultrasonic values during the heating process. And as this sheet metal is a plate, we observe some very specific and typical vibration modes, which, if you have the knowledge behind it, you can evaluate a lot of information and get a lot of information out of this. For example, the longitudinal speed of sound, which indicates the recrystallization process of this sheet steel, which is cold rolled. And as you see here, over time, we kept the temperature up to certain values. You see 680 degrees Celsius to 720. And as the temperature increases, you see an earlier finishing of the recrystallization process. So this is something which can be shown here very well. But not only the longitudinal speed of sound, but also the, as you see here, the transversal speed of sound can be evaluated. And from these also the Poisson ratio is derived, which is especially interesting for temperature above the Curie temperatures to show or to observe metallurgical events even in those high regions. An example here to observe the cold rolled steel sample, which you see on the top. It was recrystallized at 740 degrees Celsius. And what we showed here with the system is, if you have a look on the blue line, you see the recrystallization in a clear change of the longitudinal speed of sound in this area here. So we took the same sample, which was then already recrystallized, and we had it in another cycle of this temperature. So as expected, you do not see another recrystallization process, but you see the Curie temperature event in both cases. So this was the proof that this was really the recrystallization which manifested in this change of longitudinal speed of sound. So this is an important process, coming back to the energy efficiency and contribution to the day's needs. If you have a lot of accompanying elements in there, or even not a lot, but some, copper, for example, or silicon, they change the behavior of the material and they maybe shift the recrystallization temperature. And if you want to adapt your process according to the current mixture of material that you have, you can do this quick analysis at line in a thermal simulator with laser ultrasound to get the needed information. In the same system, we can also analyze cubic samples, as you see here. Those have also been heated up, and what we observed here was the austenite grain growth, which is shown in this picture here. It needs a calibration cycle, that's true. So as the colored crosses, as you see here, each are quenched samples at those temperatures, which have then been analyzed in a micrograph, and the average grain size has been determined. And after one calibration cycle, we had the needed information for the models behind it, that we could then run one single measurement, the small black dots that you see here, we estimated the the in situ grain growth in one sample during this heating curve. And you can then try out different heating curves and observe your material, how it behaves in the respective situations. A part of what I showed you before was a contribution to the metal production, or in the course of metal production mainly, but also in the processing. Laser ultrasound is very valuable. For example, with laser ultrasound, it's possible to observe or to measure the hardness penetration depth of steel parts non-destructively. You see here a microsection where we can see with the naked eye how deep the hardened layer is here. And we wouldn't have needed to make this cut actually, because if you scan here with laser ultrasound this along this line, we could then retrieve from the measurements the hardness penetration depth on every position that we would like. And as you see here, the different grain structure causes differences in the backscattering signal, which can be evaluated. On the very right-hand side, you see a machine learning algorithm, which automatically then found the interface between the hardened layer and the non-hardened layer, which was very, which was a very fast transition here. Early quality control and process optimization is often needed in joining technologies or with joining technologies. For example, if we have here a weld seam that has been scanned in the lab, and you see here a zoom of it, and after one scan over the weld seam, we could evaluate the signals, as you see here on the bottom right, and identify pores in the weld seam. This is the reference measurement of the X-ray scan. And on the right-hand side, the red, black, and green color that you see is the laser ultrasonic result, which was further evaluated to show the green areas as definitely well-welded areas. This can also be done on, you see here an automation example on spot welds. We scanned spot weld per spot weld, and we could then generate those tomographic-like images. And normally in a production process, you wouldn't need those beautiful image information, but you would probably reduce your measurement points to be even quicker. And but after all, you would be able to judge your measurement, your weld, spot weld quickly. In the early fatigue detection with laser ultrasound, it's also that laser ultrasound can help to better understand the mechanisms and thus create advanced materials to increase the fatigue life. In particular, we can predict fatigue for special cases like here with laser ultrasound. You see this buckling setup here where a sheet steel was frequently stressed, and at this area on the top you would of course expect a crack sooner or later. And what we did was a frequent measurement after for example 10,000 buckling events and compressions along this line here, and we evaluated the lamp waves. So that was what I mentioned already before. The lamp waves are the typical type of wave which propagates in sheet steel or in any sheets. And what you see here is an increase of the frequency shortly before fatigue life. So it was possible to localize and predict fatigue in this sample. And so this is also a possibility that we would have with laser ultrasound to understand the mechanisms of fatigue better and then design anti-fatigue, and to in situ and in-time structural health monitoring and fatigue prediction, and also NDT and evaluation for welded structures and joint components. I also want to show you some examples about aluminum now, because aluminum is also very energy intensive material. For example, the primary aluminum industry is responsible for 2.6% of the total greenhouse gas emissions. At least this was true for 2020. It hasn't changed a lot, I guess. And the primary industry is now laser ultrasound can't contribute too much to the primary industry, of course, but this indicates that also the aluminum processing and recycling and therefore the accompanying material characterization is very important. Applications of laser ultrasound for aluminum are, for example, the measurement and the detection of center cracks in ingots, as you see here in a through transmission measurement. The ingot was turned here, and the laser ultrasound measurement was done around the circumference. And after that, we had a reconstruction of the center crack. Sorry for the telephone. I can't. Turn it off. Okay. Sorry for that. Yeah, this was done in the lab and worked very well, but this can also be done in the factory. So in the test facility of the LKR, the Leichtmetall Kompetenzzentrum in Ranshofen, we are also doing in situ measurements and inline measurements. Laser ultrasound is also capable and suited to observe the natural aging process in aluminum. As you see here, the sample in the solution heat treatment at 480 degrees, then it has been quenched, and after that it has been observed for 24 hours. And what we saw here in those 24 hours, that the Young's modulus and the shear modulus, both depicted in this graph here, increased slowly, and we could measure them very, very accurately. So you see here we are below 1% change of those moduli, and this is very exact and also corresponds very well to the GP zone formation. Yeah, last but not least, I would like to show you this example of a cladded aluminum, which is normally used for bracing applications to enable bracing. We measured here along the surface of these samples to determine the thickness of these layers up here. This was very important for our customer. We had some samples with different cladding thicknesses, and we could distinguish them very well by evaluating the surface acoustic wave speed of sound. And our results have been within 10% of the micrographs, which is very accurate, and even the micrographs are not more accurate. All right, yeah, that was basically it for now, and so I would give back the floor to Robert to maybe he has some questions from the chat or something. I'm open for questions. Thank you.
Thank you so much, Edgar, for this very interesting talk.